Okay, got that going. So the next section that we're going over is going to be on our grammar for symbolizing the sentences that we want to talk about. And thus far, our symbolization has been extremely crude. Basically, we've just had capital letters representing entire sentences and then sentential connectives. So if I wanted to say something like, every man is an animal, or some birds like poker, I would have to say, A for every man is an animal, and some birds like poker. And that's about as granular a way we could have, as granular a way as we could have broken up that sentence, which is still very crude. Symbolizing the entire sentence like every man is an animal with just one letter. That's very crude. It doesn't give us much insight to the structure of the sentence. And the structure of the and there's a lot of structure to the sentence, every man is an animal. So that's what we're focusing on in this next chapter, is taking these sentences and breaking them down into their actual logical structure. So far, we've just been using sentential connectives and atomic sentences that we combine with sentential connectives. Everything is read or not read. How could we even symbolize a sentence like this? You might think we could have said, well, we can symbolize that as read or not read, something like that. Everything is read or everything is not read. But that's not really even what the sentence is saying. This sentence is saying everything is read or not read. It's not saying everything's read or everything's not read. It's saying everything is one or the other, read or not read. Pick a thing that's read or not read. This is true. This sentence right here is obviously false. So this still doesn't quite capture that. The only way we could capture something with this much structure is just literally with, okay, that's an atomic sentence, R, there we go, everything's read or not read. Which is not great, because there's a lot going on in here, logic-wise, that we can already see. We can see the or, we can see the not. So, one better way to break this down. So, our grammar is roughly going to be composed of 5 separate things. We're going to be using sentential connectives like we know and love. Not, and, or, implies, and if and only if are truth functional sentential connectives. We're going to be using parentheses. That's one that we've also kind of been using here and there, wherever it makes sense, using parentheses. So those 2 we've been doing. These next 3 are going to be new. We're going to start capturing the terms used in a sentence. And terms we can roughly think about as either variables or constants, but terms. And then we'll talk about predicates. Predicates, intuitively, we can think about properties or relationships between objects. Properties of objects or relationships between objects. And then finally, quantifiers, our universal quantifier and our existential quantifier, which we've come across before. So the first of these new things that we're going to knock out is terms. Terms. Intuition. Terms we can think about as being variables and constants, or combinations of variables and constants intuitively, where variables we can think about as being universal objects and constants are particular objects. Going back to Aristotle's terminology for this, what we mean by a variable, he would have called a secondary substance. Something like number. Number is a variable, or number is a secondary substance. Another example would be cows. Cows, we'd use a variable to represent cows, or cows is a secondary substance. Whereas constants are primary substances. Constants are individual particular things. I am a constant, you are a constant. Humans, we would represent with a variable. So constants and variables are what we use to compose our terms. Terms are pretty much just composed of constants and variables. That's just high-level intuition. We'll do some examples, and then we'll give an exact definition of what we mean by a term. So going back to our sentence, everything is read or not read. If we capture the terms in the sentence, the thing that we're talking about is everything, and it's read or not read. So a way that we might rewrite this sentence, explicitly capturing everything with our variable x, we might say, for every x, it's the case that x is read or x is not read. And that would be plugging the variables in to a sentence. So this and this say the same thing, we just made explicit what the variable is that we're using. No difference between what those sentences are saying. Now, you might think, going from this to this, okay, that seems to just make the sentence a lot bigger and more convoluted. Are the variables just complicating things? And the answer is no. Well, in this particular case, it may seem like it's complicating things. In general, variables make it much easier for us to talk about things. So for example, if we look at the sentence, for any numbers x, y, and z, then x times y plus z is equal to x times y plus x times z. That's using variables. If I tried to say this sentence without using variables, I'd have to say, for any three numbers, then the product of the first number with the sum of the second and the third is the same as the product of the first and the second summed with the product of the first and the third. And that would be almost impossible to understand reading that out on paper. Now, here's an example of how this notion of putting variables in and capturing terms like this is something that was kind of developed with the development of algebra. And so if you go and you read old problems, like if you were to go find an old Egyptian textbook teaching kids their arithmetic, this is how they would often word their problems. They'd say, find the number whose product with 3 is 9 greater than 6. Which is kind of hard to understand. Now if we re-represent this with our variable, find the number x, so find x, find the number, we're going to use x for our variable, find the number whose product with 3, so we want 3 times that number, is, usually means equal, 9 greater than 6 is 6 plus 9, 9 greater than 6. And so that breaks down into find x such that 3x equals 6 plus 9. This is much easier to assume. 6 plus 9, that's 15. 3 times what gives me 15? 5. 5 is the number they're looking for. So when you go read older textbooks, this is the way that they word their problems, because this development, this usefulness for capturing our variables with, or some of these terms with variables, the way that we do here, wasn't known. And it turns out to be extremely useful, and it's something that we're very interested in. So that's hopefully giving you an idea of what we mean by variables so far. Up here, x, y, and z were all variables. Here, x was a variable, 3 was a constant, 6 was a constant, 9 was a constant. So now, let's get an exact definition of a term. A term is an expression which either names or describes some object. We would think about that as a constant. If it names or describes something, then we call that a constant. Or results in the name or description of an object when the variables in the expression are replaced by names or descriptions. So that's a bit of a mouthful to consume. So a term is an expression which either names or describes some object. So if it names or describes something directly, good, it's a term. Or if it results in the name or description of something when you replace the variables with names and descriptions, with constants. So it's either a constant, or when you substitute all the variables with constants, it's a constant. That's what means to be a term. We'll do some concrete examples in this definition, and I think it'll make more sense. Yeah, let's do examples of what it's doing and then come and have a little bit more to say. So as an example of a term is an expression which names, let's start with names. I could do A is the term Isaac Newton. A now is a term because it specifically names Isaac Newton, an individual particular person. Or describes some object. The greatest mathematician. There's one and only one greatest mathematician. That is a particular person. Who the greatest mathematician is. Now, maybe you don't know, maybe I don't know, maybe we don't know who the greatest mathematician is. But the greatest mathematician is one and only one individual particular person. It names one and only one object. So this is an example of a description of an object. This is the example of a name of an object. So a term that either names or describes some object, or results in a name or description of an object when we replace the variables with names or descriptions. So here's an example. Notice that variables do not name a particular thing. So I have x is greater, I don't want to say that yet. Let's come to these examples. Let's say which of these are terms, and then we'll go back and make sense of that. So x plus 3, is this a term?
Yes.
Yes, it is a term. How do we know it's a term? This doesn't name a particular number, but when we replace the variable with a constant, pick some constant, 9, then now 9 plus 3, that's equal to 12. That is a particular number. That's one and only one thing. We know exactly what that is. All right, what about 2x is greater than 9?
Yes.
No. Because you pick some number, doesn't matter, we'll pick 7. So 2 times 7 is 14, so now it's 14 is greater than 9. That's true, but that's not naming a particular number. That's just stating something. 14 is greater than 9, that's true. But 14 is greater than 9, what number is that? It's not. It's not naming a number. So this one is not a term, because it does not name or describe something or result in the name or description of an object when we replace the variable with a name or description. Here's another one. X squared plus y squared minus 17.
Yes.
Yes. We plug in x squared, that's going to just be some number. Plug in a number, we get some number. Plus, plug in a number, we get some number. Add those together, we get a number. Subtract something, we get a number. When it's all said and done, we just have a number. This is just a long way of writing out one individual particular number when we replace the x's and y's with a particular number. So it is a term, because if we plug in a number for x and y there, then it names one and only one particular number. What about the sky is blue?
Yes.
Now, the sky is a term, but is blue, the sky is blue, what object is that talking about? It's not naming a particular object. It's describing a fact about a particular object, but the sky is a particular object. So this is one and only one object out there, one and only one thing, the sky. But the sky is blue, that's not naming an object, that's saying something about an object. The fattest man in state X.
Yes.
Yes. When we replace X with some state, then this is now naming one and only one man. So let's go over the definition one more time, and then hopefully it starts to click, because it's a big definition. All right. So a term is an expression which either names or describes some object, or results in the name or description of an object when the variables in the expression are replaced by names or descriptions. So a term is a constant, or results in a constant when we replace the variables with constants. So that's the way I'm going to use this. So I'm going to talk about in terms of variables and constants, where constants stand for names and descriptions. So it's a term if it's a constant, or if it ends up a constant when you replace all the variables with constants. As a matter of notation, we like to use lowercase letters at the end of the alphabet when we're talking about variables, and we like to use lowercase letters at the start of the alphabet when we're talking about constants. So up here, Isaac Newton, that's one individual particular person, so we use a lowercase a to represent him. The greatest mathematician ever, we used just B to represent him, because this is talking about one and only one thing. So A's and B's for our constants, for our names or descriptions, and then X, Y's, and Z's typically for our variables. And so now we could have taken a statement like Isaac Newton is the greatest mathematician, and we could have easily symbolized it with A equals B like that. Now, note, variables do not name a particular thing. For example, when I say x is greater than 3, what's x? We don't know. It could be any number of things. Okay, so we've gone over those, saying which of those are terms, and hopefully now got some pretty good intuition for what a term is. All right, so now we move on to a predicate. A predicate. Intuitively, a predicate is a property or a relationship between terms. So we know what a term is. Now, a predicate is a property of the term or a relationship between some number of terms. Could be more than 2. That's the definition used in the book. Here is a more precise definition for those that have taken a bit more logic and are ready for a more precise definition. A predicate is a proposition-valued function. It's something that, if you give it a term or some number of terms, it spits out a proposition, something that's true or false. As a matter of notation, we're going to use capital letters now to represent terms. So up to this point, we've been using capital letters to represent whole sentences. We're never going to do that anymore. From here on out, anytime we write a capital letter, we're going to be using it to represent predicate. Did I say term? Predicate. Let's see. Yes, we need to move it. Okay. So let's get an example. I still see that full column. Might be useful to reference some of those. Okay, so let's look at a simple predicate. Simple predicate is the is read predicate. This is stating a property of some term. If I say is read true or false, you can't answer that question. But if I give you a term, like this desk, then you can now answer this desk is read. Not just a term, I have to give you a constant, sorry. If I give you a particular object, so if I give you a name or a description, a constant, then you can now call your predicate true or false. So is read is a predicate. I say this desk is read, now that's something that's true or false. So going now back to our sentence, we started out with everything is read or not read. We switch that to for every x is read or not read. Now using R for the is read predicate, we can rephrase that as for every x, read applies to x or not read applies to x. And this will be how we do our notation. We do our predicate and the term our predicate is applying to right afterwards. So this would be read as for every x, R applies to x or not R applies to x. In this case, R is read, so we can read that as for every x is read, or it is not the case that x is read. All right, so with that so far, let's try some examples breaking down sentences this far. So now we're doing our some derivation, and we've got a sentence, every man is an animal, and now we want to break that down. And so how would we break that down?
For every x.
Perfect. So this one is saying, if something's a man, then it's an animal.
For every x, and is a.
Huh?
Yeah.
Almost. So we got if M applies to X, that implies A applies to X. For every X, if man applies to X, then animal applies to X. Every man is an animal. Okay, let's try another one. The sky is blue. We would just represent that as the is blue predicate applies to little s sky. And it's understood there that little s now is just a constant. So up here that was a variable, s here is a constant, it's talking about an individual particular thing. So here's the sky is blue. Frank is taller than Jack. So this is our first time where we see a predicate taking two terms. So we say the taller than predicate applies to Frank and Jack. And that's how we symbolize that.
Okay.
So your predicate, the first term that your predicate is expecting, and then the next term. And if it was a predicate that took three terms, then the next one would follow that, etc. And there's no limit on how many terms a particular predicate can take. All right. George is very fast and strong.
So G, capital G, small f and small s.
Other way. So we say the is very fast applies to George,
Oh,
and the very strong applies to George. And so that's how we symbolize that. Now, there's no reason that we couldn't have defined a predicate, W, which is the very fast and strong predicate, and say the W applies to George. We typically break it up like this, but there's no reason that we can't combine two predicates together to give us a new compound predicate. Perfectly valid. Okay, so note, a predicate is neither true nor false. We may convert it to a proposition. We may make it true or false with a constant by adding constants to it. And so once you give a predicate a constant, it is always true or false. Notice that this was true or false. George is very strong and George is very fast, that's true or false. Frank is taller than Jack, that's true or false. The sky is blue, that's true or false. This one up here if it's a man, then it's an animal. That's kind of a weird one. We can't really call that true or false yet. Give a better example of that. If I were to say something like, if it's a cow, then it produces milk. Intuitively, you might say, oh, that's something that we can call either true or false. But what is that statement saying? If it's, another way we can say that is, cows produce milk, true or false? And the problem that people have with something like that is, are you saying every cow produces milk or some cows produce milk? And it's the same thing that Aristotle called indefinite universal. Cows produce milk, in that statement, cows is an indefinite universal. It says you can't call it true or false. You need a quantifier. You need to say every cow produces milk or some cows produce milk. You can't just say cows produce milk. So this one was kind of a weird one. Man is an animal. Are we saying every man is an animal or some men are an animal? It turns out in that case, it didn't matter either way, but that just was an accident of the example. Anyways, so a predicate by itself is never true or false. We may convert it to a proposition, convert to something that's true or false when we add a predicate. Is an animal, it's not true by itself. Is a man, it's not true by itself. You need to be talking about something. Okay. Now sometimes it's annoying to represent a predicate, or to write out a predicate that is read predicate like this. And so we may symbolize a predicate with variables acting basically as placeholders. So rather than saying the is read predicate, I'm instead going to write X is read for the predicate to show you where the term would go. If we looked at the loves predicate, I'm instead going to write X loves Y to show you where the terms go. If you look at the loves both predicate, here's one where it can get kind of confusing, and so it makes more sense to say X loves both X and Y, or both Y and Z. So there's an example of a predicate that takes 3. So oftentimes we stick variables in here. It doesn't matter if we do or we don't. When we do, they're just acting as placeholders to tell us this is where the terms would go. Okay, example. Which of these are predicates? X is greater than 3.
Yes.
Yes, that is a predicate. It is not true or false right now. If we replace that X with a particular term, then it becomes either true or false. If we replace it with 5, it's true. If we replace it with 2, it's false. Now notice, if I were to say, describe this predicate, this is the is greater than 3 predicate. The X there is just acting as a placeholder. I could have just as easily said greater than 3 is a predicate. But it's convenient to have a variable in there as a placeholder. All right, 2 plus 2 equals 4.
No.
No, not a predicate. X plus Y equals Z plus 2.
Yes.
Yes, and this would be a hard one to say in words. It would be the sums together to get the third and 2 predicate. So sometimes it gets harder and harder to say in words, but really easy for us to symbolize it. So that's convenience of symbolizing it there. So that's what predicates are. They state properties or relationships between things or between terms, and in and of themselves we cannot call them true or false. It isn't until we give them a constant that we can call them true or false, thus far. We're going to see how we can also give them a quantifier when we talk about quantifiers. So moving on to quantifiers now. Our quantifiers we have broken up into 2 types. We have our universal quantifier and our existential quantifier. Our universal quantifier, this upside down A, we usually read as for all, for each, or for every, but there's tons of English ways we can read it. And the existential quantifier, we almost always read as there exists. And we almost always say there exists such that afterwards in English. Makes it read better. You'll get used to saying that as you use this. It becomes pretty natural. So, now, we can convert a predicate to a proposition by either replacing the variables with constants. That's one way. If I take the variable and I replace it with constant, it now becomes true or false. If I take these variables, replace them with constants, it now becomes true or false. That's one way. Or by adding the appropriate quantifiers. So let's see some examples of how adding quantifiers can convert a predicate into a proposition, can turn it into something true or false. So we're going to look at some predicates here and add some quantifiers to see it happen. So we'll start with the loved predicate, x loved y. X loved y, we can't call that true or false. But now, if I come down here and I add a universal quantifier and an existential quantifier and read this, let's read what it says. It says for every x, there exists a y such that x loved y. We always say such that after we read the existential. So I'm going to read that one more time. For every x, or for each x, or for all x, however you want to read that, for every x, there exists a y. After that, we always say such that, after an existential quantifier, such that x loved y. In plain English, this is saying for, well, not quite plain, we'll break it down to plain English. This is saying for every person, there exists another person, such that the first person loved that person. Or it says everybody has loved somebody. This is essentially what that's saying. Everybody has loved somebody. So now let's move on to this one. X plus y is equal to z plus 2. That's just a predicate. But now I say there exists an x and there exists a y and there exists a z such that x plus y is equal to z plus 2. Okay, now this is a true statement. This is something that we can call true. There are an x and a y and a z such that this is true. For example, x could be 4, y could be 4, z could be 6. 4 plus 4 is equal to 6 plus 2. So now this was true. X is a miser. We can add an existential quantifier on it. And now, most likely a true statement. There exists someone out there who is a miser. There exists a person such that they are a miser. There exists x such that x is a miser. And then greater than 3 predicate, add an existential quantifier, now that makes it true. There exists an x such that x is greater than 3. That's not true. If I were to switch this out here and say for all x, x is greater than 3, still a proposition, but it's false. Similarly, let's look at this one for a second and play around with the quantifiers a little bit. This one is saying everybody, for each person, there exists someone else such that the first person loved them. Notice what happens if we switch the quantifiers here. Now what does it say? If I put the existential there and the for all there, now that's saying there exists a person such that for any other person, the first person has loved them. This is saying there is someone who has loved everyone. Whereas before it was saying everyone loved someone. So order definitely matters with these quantifiers. And I can do something else like say everybody loved everybody. Or something like this, which essentially says there exists 2 people that have loved each other. Or no, not even that. There exists someone who has loved someone. Maybe the love wasn't returned, who knows. So that's using quantifiers to convert predicates to propositions. You missed the predicates.
My bad. Sorry. It went longer than I thought it would.
All right. So now, these are some examples I typically do with my discrete math students to help them grasp these quantifiers. So now you're just going to tell me true or false for reading these. So this says for all x for all y, x plus y equals 0. True, right? The sum of any 2 numbers is 0.
No.
5 plus 9, 0.
Okay.
10,000 plus 94, 0. No, this is false. Right?
Yep.
Okay, let's try this one. For every x, there exists a y such that x plus y equals 0.
Yes.
Okay, that one's true. Pick any x you want for every x. I say 100. There exists a y, yes, negative 100, such that their sum is 0. Okay, so that was true. Let's try the next one. There exists an x such that for every y, x plus y equals 0.
Nope.
There is no magic x out there such that no matter what you add to it, it's always 0. That x does not exist. So this one is false. There does not exist some x such that for any y, x plus y equals 0. All right, let's try the last one. There exists an x and there exists a y such that x plus y equals 0.
Yep.
Yes, can we find 2 numbers whose sum is 0? Yeah, easily. 0 and 0. 1 and negative 1, 2 and negative 2. All right, now let's switch all these to multiplies and do it again. For every x and for every y, x times y equals 0. True or false?
False.
False. For every x, there exists a y such that x times y equals 0.
True.
True. There exists an x such that for every y, x times y equals 0.
True.
In this case, it is true. What's the magic x? 0. 0 is the magic x such that no matter what y you choose, when you take their product, you get 0. And then finally, there exists an x and y such that their product is equal to 0.
True.
True. Okay. So that's getting comfortable with quantifiers. So, the symbols we'll be using in our grammar now. Truth functionals and potential connectives.
Okay.
Parentheses.
Okay, yeah.
Terms, which will be variables or constants, or combinations of the two.
Okay.
Predicates, things that result in something true or false when you give them a term.
Can I get an example of that?
Yes. Let's do examples of predicates really quick again. Is red is a predicate. True or false? Is red. Doesn't make sense.
Yeah, it doesn't.
True or false? My face is red. Now you can answer the question when I give you a particular object to talk about, when I give you a particular constant.
Yeah, you can.
I say, your shirt is red.
Yes.
Okay, I say, horses is red.
Not really.
You can't really answer that.
Yeah.
So I need to give you a particular thing, one and only one particular thing, which we call a constant. So I'm talking about an individual particular object. That's what I will mean by the word constant.
Okay.
So a predicate becomes a proposition when you give it a constant. When you give it an individual particular thing to talk about.
So predicate is red.
Is red is an example of a predicate.
Okay, yeah.
Is an animal is another example of a predicate.
Okay.
Let's actually redo these really quick. Just to help you get it really quick. So, we're now symbolizing these. We are now going to use capital letters to capture predicates.
Okay.
So we have the statement, every man is an animal. What is that statement saying? Now, you didn't hear us for the first part. First thing we do is we capture the variable in there. The variable we're going to say for every x, and use x as our variable. For every x, now what is the statement saying?
X is in A. X.
This is saying if x is a man, then x is an animal, right?
Yeah.
So it's saying if the is man predicate applies to x, and that's how we write it. Capital letters for our predicate, and then the term that our predicate's talking about comes right afterwards.
Okay.
Because a predicate always has to be talking about a term. So for every x, is animal applying to x implies, oh sorry, man applying to x implies animal applies to x.
Man is a.
Is man is a predicate. Is man
Okay.
is an animal.
Why would you not just call X man? Like say X is a man instead of calling X something that is man.
Right here, what is this statement saying? This statement is saying for everything in existence, if it's a man, then it's an animal. For every x, if x is a man, then x is an animal. Okay, the sky is blue. What's our predicate in here?
Is blue.
Is blue, and the sky is what we're talking about. So we would say the is blue predicate, maybe represent that with capital B, applies to sky, a constant.
Why are you not calling sky S? It's something in the universe. So
The sky is right there.
what you said before is out of everything in the universe, if it's a man, then it's an animal. So out of everything in the universe, if it's a sky, then it's blue.
This isn't saying every sky is blue. This is saying one and only one individual particular thing.
I see.
Up here, this is talking about a variable. Down here, we're talking about a constant. The sky is a constant. All right, let's try another one. Frank is taller than Jack.
Okay.
What's our predicate there?
Is taller.
Is taller than. The is taller than predicate, which we can represent that with capital T. And that is applying to the two constants, Frank and Jack. So that's how we symbolize that. Taller than applies to Frank and Jack.
And the order matters.
And the order matters.
Okay.
This is what comes first in our predicate, this is what comes second, and there's no reason that a predicate could take any number of terms.
Could you go FTJ?
That will be notation that we use in the special case where a predicate takes exactly two terms. And we will switch to start using FTJ. And that is notation. But for now, this is the way we're going to symbolize it. Alright, try this one. George is very fast and strong. What is our predicate?
Is very fast and strong.
Well, you can kind of see two predicates in there, right?
Is very fast, is very strong.
Is very fast is a predicate, so we'll represent that with F. Is very strong is a predicate, so we'll represent that with S. Okay, what are we saying?
George at the very end. George is both of those.
Right. George, very fast applies to George, and very strong applies to George.
Yeah.
And then we need to and them together. So notice up until now, if I were to give you a statement like George is very fast and strong, before you would have had to just represent that statement as one letter, something like, I don't know, capital G is how we would have represented that in a derivation before. Now we're getting more fine-tuned, and we're breaking it up into its actual structure. So now that's big picture what we're doing here. We're taking sentences, and we're breaking them up into their logical structure. We're identifying not only the intentional connectives, but we're also identifying the terms, the predicates, and the quantifiers. Okay. So you're already comfortable with quantifiers, universal quantifier, existential quantifier.
Yep.
Okay? And so the thing that we notice here is how one way that you can convert a predicate into a proposition, one way you can take a predicate and make it something that's true or false, is to give it a constant, give it the constants it needs.
Okay.
That's one way to do it. A second way we can do it is to give it the appropriate number of quantifiers. So for example, looking at x loved y. True or false? You can't answer that. Now if I give you Romeo and Juliet, then you can answer yes, Romeo loved Juliet. And you can call that true if I give you the appropriate number of constants. That's one way to do it. Or I could do something like this, and I can give it to existential quantifiers. And I can say there exists a person X and a person Y such that X loved Y. That's just saying somebody has loved somebody, right?
Yeah.
Now we could have used any two combinations of quantifiers that we wanted here and it still would have worked. I could have just as easily put a for all here. Now what is this statement saying?
For all X, or there's every man loves this guy.
For every X, there exists a Y such that X has loved Y.
Yeah.
Or it's basically saying everybody has loved somebody.
I see that,
Okay. Well, if I swap the order there, it says the same thing still, right? Order doesn't matter. What does it say now?
Somebody loves everybody.
Somebody has loved everybody. There exists someone who loves everyone. So that's very different. So order does matter.
Yep.
And then finally, I could replace it with two universal quantifiers. And it's basically saying everybody loves everybody. Okay. So that was the example. And we can do the same things with each of these predicates. We give it the appropriate number of quantifiers, and now it becomes something that's either true or false. And we did those examples. Okay, let's move on to the whiteboard. Try and get it all in one go so I don't have to mess with it after the fact. Okay. Yeah, that looks awful. Alright. Can't mess with it. One of these is good. Alright. Coming over here. Now, oh, I didn't finish off our main example. I can't believe I didn't finish it off. Our main example, so we kept looking at the sentence over and over again. We started out with the sentence, everything is red or not red.
Okay.
Then we went to for every x is red or x is not red.
Okay.
And then we went to for every x, either red applies to x or not red applies to x. And now finally, if we were to give our final symbolization to that statement, it would be for all x, red applies to x or not red applies to x. And so what started out as one atomic sentence, everything is red or not red. Notice we can't break that up anymore.
Yeah.
There's no way for us to break that up. You might be tempted to say, can't we break this up into red or not red?
We have to get to the every.
Yeah, we don't have the every there. And so using our old way, we couldn't break this up into two sentences. If we tried to do that, this is a sentence, everything's red, this is a sentence, everything's not red, then that doesn't capture what this is saying. This isn't saying everything's red or everything's not red. This is saying everything is red or not red. It's not saying we live in a universe where everything's red or we live in a universe where nothing's red. It's saying in our universe, everything is red or not red. So it says something very different. So we couldn't symbolize it with sentences like this before. This was an atomic sentence before. There was no more fine-tuned for us way to break that up. We would have to just represent that with a capital R in our earlier derivations. Now, we're representing it like this, and we're capturing a lot of structure in that sentence.
Yep.
So that's what we've been doing, big picture, throughout this whole chapter. Going from, rather than taking the sentence like everything is red or not red and representing that with just a big R, representing the whole sentence, now we capture all that structure. And there was a ton of structure to it. And all that structure means something. And so we're going to now be able to do an analysis of its structure and talk about what it means. So now that we know how to, and that's as much as we're going to break these up. So that's it for breaking up English sentences. So now we're going to break down a bunch of English sentences and get down to their fundamental structure. What exactly are they saying? And try and get comfortable with this. So I give you the first one. All men are animals. That means for all x, if x is a man, then x is an animal.
Yep.
All right, so let's move on to the next one. All freshmen are intelligent. How would we write that one?
For all x, if x is, so yeah, if x is a freshman, then they are ix. They're intelligent.
And the way you say that is for all x, f applying to x implies I applies to x. All right, let's try this one. Not all freshmen are intelligent. Okay, how are we going to do that one?
Wouldn't that be there exists?
Not sure if I jumped to the existential quantifier here or not, because I got you guys pretty comfortable with that earlier than the author does. So let me try and guess at the author's intent here. Perfect. Yes, we did go to the existential quantifier. Okay. And we did just put negation in front. So perfect. Keep going with what you're saying. There exists x such that.
F of x. Well, would you do that? Because it's in. Never mind, I get it.
There exists x such that.
F of x applies to I of x, or implies I of x.
Such that, or implies I of x. There exists someone such that if they're a freshman, then they're not then they're intelligent.
I said not all freshmen are intelligent.
Not all freshmen are intelligent. There exists someone such that if they're a freshman, they're intelligent. That says not everyone. That says not all freshmen are intelligent.
Oh, if you put not intelligent.
Oh. Not intelligent applies to x. There exists an x such that if they're a freshman, then they're not intelligent.
Yeah.
Does that say the same thing as not all freshmen are intelligent?
You have to say.
Let's say that we live in a universe full of just intelligent freshmen and one rock. Is it true that there exists something in that universe, namely the rock, such that if that rock is a freshman, then it's not intelligent? Yes, it's vacuously true.
Okay.
Is it vacuously true that if a rock is a freshman, it's not intelligent?
Yep.
Yes, that's vacuously true. So this does not say not all freshmen are intelligent. How would you prove me wrong? I say all freshmen are intelligent. And you say that's not true. How would you prove me wrong?
There exists freshmen that's not intelligent.
How would you in the real world prove me wrong? Forget this for a second. I say all freshmen are intelligent. How would you prove me wrong?
My brother Zach.
You would go grab an individual person and you would say, here's someone who's a freshman and they're not intelligent.
Yep.
So you're looking for someone who's a freshman and not intelligent. That's how you prove it me wrong. There exists X such that X is a freshman and X is not intelligent.
The rock.
The rock is not a freshman.
Yeah, but if it were a freshman, I mean, it'd still be.
Then it wouldn't be a rock anymore. It'd be a freshman.
We'll have to use that.
Rocks can't be freshmen. Before, when you had it like this, does there exist something such that if it were a freshman it would be unintelligent? Sure, a rock. Because it's not a freshman. It's vacuously true.
Oh, I see where you're going back.
Go back to, if Donnie's a purple elephant, rainbows come out of the center of the sun.
Yeah. Yeah, I see that. Implies that messed up.
Right. So that's not what it's saying. It's saying this. There exists someone who is a freshman and is not intelligent. That's what we mean by not all freshmen are intelligent. All right. Now let's go on to the next one. No freshmen are intelligent.
That's the same thing as not all freshmen.
It says the same thing. So this is saying that for all X, or there exists an X such that they're a freshman and they're not intelligent. Right? This says no freshman is intelligent.
Oh, yeah, it is different.
Oh, no, it is different. Okay, that didn't work.
I was gonna say it's the, for every X.
For every X,
There is a freshman who is not. For every X, there's FX implies.
implies not intelligent. Perfect. Now that says for every person, for everything, if you're a freshman, you're not intelligent. For all X, if it's a freshman, then it's not intelligent. No freshmen are intelligent.
That's so tricky, but I get it, man.
Yeah, none of this stuff is trivial the first time you come across it. It's one of those things that you train your brain to think that way, and once you get used to it, you get used to it, but yeah. What did I think you were going to do there? Let me see my notes. Ah, right. That is what I thought you were going to do. Okay. So we got this right? Some freshmen are intelligent. There exists X such that if X were a freshman, then they'd be intelligent. Let's go back to my universe. All we have are intelligent freshmen and a rock. Let's think about the rock. Does there... Sorry, I'm not sure I said my universe right. Universe of just unintelligent freshmen and a rock. Is it now true that there exists something in the universe, namely a rock, such that if it's a freshman, it's intelligent?
No? Rocks aren't intelligent.
Oh, that's why I said some forks are intelligent. Think about it this way. Is the statement some forks are intelligent true? No. Okay, so you know that one's obviously false.
Yeah.
Notice how you would symbolize it. You'd symbolize it the exact same way.
Yep.
So you're saying some forks are intelligent. That means that there exists X such that if it's a fork, it's intelligent.
Let's see. So is it and?
Perfect. So it's and. So some freshmen are intelligent means that there exists someone such that they're a freshman and they're intelligent. And it's very tempting to use that implies in these existential interpretations. It's a very easy trap to fall for. So some freshmen are intelligent means that there exists a freshman such that. And I don't know, it always helps me to think, how would I know if that's true? Or how would I know if it's false when it's a don't or a not? How would I know that some freshmen are intelligent? I need to go find a particular freshman who's intelligent. That's how I know. And how would I know not all freshmen are intelligent? I need to go find some particular freshman who's not intelligent. That's how I know. So that's personally the bit of psychological thinking I go through to make it appeal to my intuition better. Alright, let's keep going. Adam is not married to anyone. How do we symbolize that one?
Adam's a constant.
Adam's a constant.
Is not married.
Is married with a negative.
Yeah. Kate is married.
So tell me what's right.
So A. Let's do M. Not M.
You want not M.
Just put it there.
Just put it there and leave it.
We'll figure out the way around.
Alright.
What do you do with that preposition?
Not married. We got that.
To anyone?
Who's not married to anyone?
Adam.
Okay, so Adam isn't married to anyone. We don't know who anyone is. As a general rule, I'm not sure if you were here, we're going to use lowercase letters at the start of the alphabet for constants and lowercase letters at the end of the alphabet for variables. Adam's a constant, X is a variable.
Okay, so
Because married applies to two terms, Adam and X. Okay? Now what?
it's done.
It's done.
Okay. For not all.
True or false? Not married, Adam to X.
Okay. Put Adam before the not married.
Well, no, you're still fine. One way we can read this is Adam's not married to X. Is that true?
And X is anyone, so yeah, Adam's not married to anyone.
No, we said Adam's not married to X. True or false? Let me give you another one. X is greater than 3. True or false?
So make.
It's not true or false.
So
You
anyone's
needed
not
that
married.
X.
Oh, quantifier.
Or you need a quantifier.
I see,
Oh.
okay.
What's the quantifier we could use?
Anyone is there exists. Anyone.
Anyone is there exists. So there exists someone such that Adam is not married to.
For all.
For all. There we go.
And that's true.
For all X, it is not the case that married applies to Adam and X.
Yeah.
Or in other words, Adam is not married to anyone.
Okay, I see that.
All right, yeah. These can be a little bit of work. Let's try another one. Some freshmen date Elizabeth.
Is freshman a variable?
We're going to use a variable to capture freshmen, and we're going to use a constant to capture Elizabeth.
Okay. So date is the
Date is a predicate, perfect, and it applies to,
Elizabeth.
we say freshman and Elizabeth, right?
Yeah, that way for in it there exists freshman?
There exists X. You're saying like this?
Except it's not there exists, but some there exists. What is some?
I don't know. What is some?
There exists a freshman such as.
There exists X,
There exists X.
such that what?
Such that.
How would you know that some freshmen date Elizabeth? How would you prove that to me?
By bringing one up.
You would go find a person and tell me what you would know about that
So there
person.
exists is right.
What would you know about that person?
They date Elizabeth.
And
They're freshmen.
that they're a freshman.
Oh.
You need to find someone who's a freshman that dates Elizabeth.
I see.
So there needs to exist an X such that freshman applies to X and dates applies to X and Elizabeth.
But that's just
There exists X such that X is a freshman and dates applies to freshman and Elizabeth.
That changing the sentence though.
No, that's saying some freshman date Elizabeth.
It's getting rid of the plurality.
Multiple people can do it. This doesn't say multiple people can't. This says at least one. That you're making a good point for English here. Always and forever here, some will mean at least one.
Okay.
Some will never guarantee at least two. Okay. This was more precise stuff. I don't know, we need to go over it. I'll say it once. But if you don't understand what I'm saying here, you're perfectly fine. More precise definition. You might be bothered by the fact that we threw this universal quantifier in here and never explicitly defined it, and the author of this book doesn't bother because it's an introductory logic book, but we could give it an explicit definition, and here's how we would do that. So this is not the book, this is me adding on. Let P be any predicate. Then for all x, P of x is a proposition, so it is something that we can call true or false, and it's true if and only if P is true independent of x. So regardless of what x is, if P is always true, then we call this whole thing true. For example, if P were the predicate, x is less than or equal to x. Is that always true?
Yeah.
Yeah, so then we can go ahead and say this is a proposition and it's always true.
Okay.
On the other hand,
Yeah.
if we said x is less than or equal to 2, that's a proposition, but it's false. It's still a proposition.
Yep.
So let P be any predicate, then for all x, P of x is a proposition, is something that we can call true or false. And the way that we know to call it true is if it's true independent of what x is. Otherwise we call it false. So that would be an explicit way that we could define what the symbol means. And then we could explicitly define our existential quantifier. To say that there exists x, P of x, is to say it is not the case that for all x, not P of x. To say that there exists a white duck is to say that it is not the case that for every duck, it is not white. Or let's use pink, since we're using a P there, and it might be easier for you to follow. There exists a pink duck. Says the same thing as it is not the case that every duck is not pink. So that would be an explicit definition that we can give to the existential quantifier. And that's how you can explicitly define them if you want to. Again, the author doesn't do it. If you just have good intuition for it, you did enough for the purposes of this class. Okay, next topic, atomic formula. Now, an atomic formula is a predicate together with the appropriate number of terms. A predicate together with the appropriate number of terms. Here's a predicate, R. Maybe this is the is red predicate. And little a there, since it's little a, that's a constant, so that's going to be like Chandler's shirt. So little a is Chandler's shirt, the is red predicate. Here is an atomic formula. In this case, it happens to also be a proposition. It happens to be something we can call true or false.
Can't you have the predicate without the A?
Yeah, R, that's a predicate, but now it doesn't have the appropriate, if this is an is red predicate, we don't have the appropriate number of terms.
So it's not atomic formula.
So it's not an atomic formula.
Okay,
We either need to add A, we're saying a particular thing is red, or we're saying, or put X there for some variable. X is red. Now, if we put X is red, that's not something true or false,
Yeah.
but it is a predicate with the appropriate number of terms.
So it's an atomic formula.
So it's an atomic formula. Here's another one. This is the greater than 3 predicate together with X.
And that's not true or false, but it's atomic.
It's not true or false, but it is an atomic formula. We have our predicate, greater than, or less than, that one's greater than with the appropriate number of terms. Or we can think about the predicate as greater than 3 with the appropriate number of terms. X is blue. Again, predicate with the appropriate number of terms. Is blue, and a term there. In that case, a variable, doesn't matter.
Yeah.
So we're not, a formula, an atomic formula isn't necessarily something that's true or false. It's just a predicate together with the appropriate number of terms. Oh, that was symbolizing stuff from over there. So that's nothing to do with right here. Okay, so now we're going to come up with a recursive definition for what we mean by formula. And anything's a formula as long as it satisfies one of these top three rules. No expression is a formula otherwise. So these are the rules that tell us if it's a formula. Number one, every atomic formula is a formula. So each of these things are a formula. Number two, if R and S are formulas, so are not R, R and S, RRS, R implies S, and R is logically equivalent to S. In other words, take the appropriate number of formulas and apply our truth functional sentential connectives to it, and it's still a formula. I've got some formula, I knot it, still a formula. I got two formulas and I add them together, still a formula.
Does it have to be truth functional?
All these are truth functional sentential connectives, and we're only focusing on those five.
Oh, it's point distance.
So X is blue, since that's a formula, I can come along and say, not the whole thing, not X is blue, and it's still a formula. And I can say, X is greater than 3, and not X is blue, and it's still a formula. That was a formula, this was a formula, I added them together, still a formula. Last thing we can do, if R is a formula and X is a variable, then for all X, our formula is still a formula, and there exists an X such that our formula are still a formula. So take formulas, put the universal quantifier on it, or the existential quantifier on it, still a formula. So I've got this thing right here, X is greater than 3 and not X is blue. I can come onto this and I can say, maybe put square brackets, I can come onto this and I can say, there exists an X such that X is greater than 3 and X is not blue. Still a formula. No expression is a formula otherwise. So here's some expression. Is this a formula?
Should be, yeah.
No, it's a bunch of nonsense. There's no way I can start with the formula and apply these rules to it and get this thing.
They're all atomic formulas.
X equals Y, that's an atomic formula.
Yeah.
Okay. I did implies here, so the other thing over here better be a formula. Or can only or two formulas together, so this better be a formula by itself.
I see the problem.
I can't start with the atomic formula and apply these rules to get this nonsense.
It's okay. Well, the only reason it's not is because it implies and or can't do that.
Get rid of that. Now is it an atomic formula?
Yeah. Oh, not atomic.
Sorry, now is it a formula?
Yes.
No, there's no way to get that.
Why? Just have to start with X and make X equal Y.
Okay, X equals Y, that's an atomic formula.
Yeah.
Okay. Implies is something that we can do to two formulas.
Yep.
So the thing over here has to also be a formula.
Yeah.
The only way the thing over here can be a formula is if we start with an atomic formula and we start adding these things to it.
Is it because it's missing parentheses?
No, there's nothing atomic over here to start with.
It's
A quantifier can only be added on to an existing formula. There's no formula here. This quantifier can only be added on to an existing formula. There's no formula here. This logically equivalent operator can only take two formulas. So it's a bunch of nonsense. So following these rules, we're not going to be able to generate nonsense like this. And it turns out we're only going to be able to generate completely meaningful things that we can ultimately call true or false. Almost. One more restriction there. But so that's what we mean by formula. Okay. Now, if there's a quantifier in a formula, it's going to have what we call the scope of the quantifier. Maybe you read for this. The scope of a quantifier is the quantifier together with the smallest formula immediately following it. So looking at the scope of this. So here we have a quantifier. So its scope is the quantifier together with the smallest formula immediately following it. Is a predicate by itself a formula? Is m by itself a formula? No, you need the appropriate number of terms. So mx is a formula.
Oh, that's what I meant. Yeah, I thought you were saying MX. Yeah.
No, just m. So we gotta go from here all the way to x. Okay, we got the smallest formula. Immediately following our quantifier. That's its scope.
Okay.
Let's try the next one. We're always gonna look at the there exists x. There exists x. Now we gotta do the smallest formula immediately following it.
Okay. X greater than Y.
X is greater than y is a formula, but we have this parenthesis here. And so we're not going to be able to finish our formula until we close off that parenthesis.
Oh, so we have to go all the way through.
So in this case, the there exists x applies to this whole thing.
What about, why are we not doing that for every?
Huh?
How does for every apply?
Well, I'm just talking about the scope of the there exists x each time. So we're looking at the same quantifier in each of these expressions, talking about scope. But you're right that the for all y has a scope across that whole thing. All right, let's look at this one. There exists x. Tell me when to stop.
Keep going to the end.
Keep going to the end. Yeah, because we're not going to have a formula with the for all y until we finish this. Then we got a formula. That's the only way we can finish off what this goes to. And so yeah, we have to go all the way to the end. Let's try this one.
And stop.
All right, perfect. So this right here is a formula. That's a formula. So that's the smallest formula immediately following x.
Okay.
Notice that this and this are identical. The only difference is got rid of the square braces. So parentheses matter. And oftentimes, we use parentheses to make the scope abundantly clear. And you could have almost guessed without me even defining what the scope was. If I just asked you, what does the quantifier here apply to? Does it apply to this term or just this term? You probably would guess, no, it's just to this term. And same here, you would have said that x is talking about the whole thing. That is talking about the whole thing. Here you would have said, it's just talking about this. So probably would have guessed it correct to begin with. Okay, so now, a particular occurrence of a variable in some formula. A particular occurrence of a variable in some formula is bound if and only if it occurs in the scope of a quantifier of the same variable, otherwise it's free. X here is free because there's no quantifier talking about this x. It's not in the scope of any quantifier.
Oh, I see. Yeah.
This occurrence of x is bound because it occurs in the scope of some quantifier with the same variable.
Yeah.
So, an occurrence of a variable is bound if it occurs in the scope of a quantifier of the same variable, otherwise it's free. That's an occurrence of a variable. This is a bound occurrence, this is a free occurrence of the same variable. Now, a variable, talking about the whole variable now in the formula, a variable is free if and only if at least one of its occurrences is free, and it's bound if and only if at least one of its occurrences is bound. No, a variable can be both free and bound. In this expression, x is both a free variable and a bound variable. All right, in this expression, is x a free variable?
I'm not even seeing what's going on. No, it's not.
This says there exists a y such that x is less than y and y plus 2 equals 6.
Yeah, it's not.
Is x a free variable?
Am I wrong?
Does it occur in the scope of a quantifier
Yes.
of the same variable?
Oh. Is that what you mean? Oh. I see.
Oh!
Yep.
So in this, x is free.
Yeah, I see that.
What about y? Is y free?
No.
Yes!
It is, but it's bound.
It's bound in this occurrence, but it's free in this occurrence. So y is a free variable. It's also a bound variable,
Okay.
but it's a free variable too.
Seeing that, yeah.
So this occurrence of this variable is free. This occurrence of this variable is bound. This occurrence of this variable is free. Okay. So finally now we are a definition of a sentence. A sentence is a formula with no free variables. Now I told you that I basically am using sentence and proposition interchangeably in this class, and I can't help it, I'm going to do that. Strictly speaking, a sentence is a type of proposition. So every sentence is a proposition, not every proposition is necessarily a sentence.
Every sentence can be called true or false.
Every sentence is true or false.
And this.
Yes.
Not in English.
Not in English. So for this author, if you're reading the way the author used a sentence in this book, it's the same way I typically say proposition because I can't help it. We're talking about propositional logic. But, so every sentence is a proposition. So it's okay that when I'm talking about a sentence, I keep saying proposition. But strictly speaking, the inverse isn't true. But that's kind of nitpicking. For the purposes of this class, you can basically think about them as interchangeable and you're going to be fine. So a sentence proposition, basically the same thing. A sentence is a formula with no free variables. It will always be true or false.
Okay.
Because it's going to be a formula, and no free variables means you always have the appropriate number of quantifiers. And so you're going to convert your predicate to something that's true or false through proposition. All right. So now, we're just going to do one example with a big sentence and try to wrap our heads around it.
See if it's formula. Oh, see if
We're going to break it down. Look at its grammar. All right. It says, if one instant of time is after a second, then there is an instant of time after the second and before the first. If one instant of time is after a second, then there is an instant of time after the second and before the first.
that is true.
Now, hopefully no, this is true, and it's true just because that's the way time works. But
Okay.
hopefully that's a big enough sentence that when you read that, you feel like, what? And if I ask you, break that down for me, hopefully you're a little bit stumped. Okay, so first trick to do is when you read that and you get a little bit stumped, rewrite it, plugging in the variables, and that usually helps clear a lot of things up. So I'm going to rewrite this now, this time with variables. If an instant of time x is after an instant of time y, then there is an instant of time z such that z is after y and z is before x.
That's what it means.
Yeah, let's break this up. We're saying here's an instant of time. If an instant of time x is after an instant of time y, so here's y, here's x on our timeline going forward. Then there is an instant of time z such that z is after y and z is before x. So if you have two instances of time, there's an instant of time between them.
That's so simple. The problem is you said second, and not two different seconds.
If one instant of time is after a second,
Oh, it's not the same thing.
then there is an instant of time after the second and before the first.
Okay, yeah. I get that sentence.
Now, let's try to symbolize this now.
Would it be smart to just start with writing the implied arrow? Because that separates it.
Implied arrow separates it. Okay. Start with the first time.
And then if one instant of time is after a second, is after, is
Yeah, let's start with the first part of the sentence. If instant of time x is after instant of time y, let's break that up. What is that saying so far?
instant of time x
What are our predicates in there?
is after. And would be instant of time?
Instant of time is a predicate.
Yeah.
So we're saying x is an instant of time, we're saying y is an instant of time, and we're saying x is after y. You with me? So we're saying instant of time applies to x, and instant of time applies to y, and after applies to x and y. X is after y.
That means there exists for x and y.
Right, so that is if, so we got our antecedent, then you're saying we're on the there exists, So there exists an instant of time z, so there exists z such that what?
That I z
Z is an instant of time, so we have iz, and
is after. Then there is an instant time z such that, how do you show such that? Dot dot.
such that. That's what we say after every time we finish an existential quantifier. So we don't need to symbolize that here. There is a z such that, and then this.
And then just tell what z is, yeah.
Such that instant of time applies to z, and what else do we know about z?
Z is after, so az,
So after applies to
z and y,
z and y. Z is after y, and what else?
and z next.
And
A,
what?
Z next.
And after applies to z and x.
No, before.
Before
V-
is our
V
other
applies
predicate.
Z next.
Before applies to z and x. Alright, so let's read what this says. It says if x is an instant of time and y is an instant of time, and x is after y, then there exists z such that z is an instant of time, and z is after y, and z is before x.
That's true.
And that's what this statement is saying, right?
Yep.
This right here, is this a sentence? Is this something we can call true or false?
Yeah.
No. Because that's a free occurrence of x, that's a free occurrence of y, that's a free occurrence of
That's what I
xy.
was thinking, we should put quantifiers in that first one.
Yeah, somehow we need quantifiers for this whole thing.
Just don't get how.
And so now we come to one of the problems in English. In English, a universal quantifier is often given idiomatically. You know what an idiom is?
No.
It's raining cats and dogs. If I say it's raining cats and dogs, what did I just tell you? Did I mean literally cats and dogs are falling from the sky?
No, just
No.
drugs.
So idiomatically means it's not literally given in the expression of the words. So it's often the case that in English, our universal quantifiers are not literally given to us. And in a sense, we have to guess at what we think the author meant. The example I use is cows produce milk. What is that saying if we were trying to just break down this sentence?
All cows produce milk.
Yeah, you naturally want to say that this means for all x, if being a cow applies to x, then producing milk applies to x. Notice, strictly speaking, all this is saying is if it's a cow, then it produces milk.
Yeah.
Strictly speaking, that's all that says.
Then it's not a sentence or a form.
Right, so strictly speaking, cows produce milk is a predicate. But in English, since we are going to be working with English sentences and trying to look for their logical structure, we say typically what people meant is they meant to put a universal quantifier in front of it. And so it is almost the case that when someone gives you just a predicate, if you just keep adding the appropriate number of universal quantifiers, you'll get at what they're saying. So we can come to this whole thing, and if we add
For all x
for all x
and y.
and for all y, then now we would probably most likely agree that that's what the sentence is saying.
Yeah.
Although we can never be for sure right and wrong because it's not explicitly saying it. It didn't say for any two instances of times it's the case. But we're assuming that's what it meant. So this says for any two instances of time, for all x and for all y, if x is an instant of time and y is an instant of time, and x is after y, then there exists a third instant of time such that it's after y and before x. So, strictly speaking, was this a sentence? No. It needs the quantifiers. And this is one of the most useful things to understand about going from the English language to a logical understanding of what the language is saying, because it's one of the most common things that people do and people argue about. They get in these disagreements, these arguments. A lot of the time, it's because they're not talking about a proposition. They're talking about a predicate. They're talking about a statement like cows produce milk. Sorry, I even just called that a statement. So that's your fault. They're talking about a predicate like cows produce milk. And talking about it as though it's true or false. A famous one in philosophy is the ends justify the means. That's one that there's a lot of conversation about. True or false? The ends justify the means. What's the answer? The answer is it's an invalid question. You know what an invalid question is? It's a question with a false premise baked in. You did this as a kid. You go ask some other kid, you say, do your parents know you wear ballerina shoes? They say no. Well, you better go tell them. It's an invalid question. It has a false premise baked in. What's the false premise? The false premise is, oh, sorry, if we ask this a question, I didn't make this a question, I thought I did. I kept writing it as a question. So when I ask you, do the ends justify the means? The answer is, that's an invalid question. That's a false premise baked in. What's the false premise? You're saying the ends justify the means is a proposition. It's not a proposition. What are you saying? Are you saying that for every ends and for every means, the ends justify the means? Are you saying that for every ends there exist a means, such that the ends justify the means? Are you saying that there exists an end such that for every means, the ends justify the means? Or are you saying that there exist an ends and there exist a means, such that the ends justify the means? And those are four very different statements. And which of those four they're talking about have to be argued in very different ways. So, it's a bad question. It's one of the reasons I have very little respect for most modern philosophers, and have a ton of respect for Aristotle. Because Aristotle did not do stuff like this. He knew better. And modern philosophers do garbage like this all the time. And the only recourse of analysis they have is logic. And so a philosopher not knowing his logic, that's kind of like a physicist not knowing his differential equations. What are you doing? So, don't argue about predicates. Only argue about propositions. Okay. Let's move on now to some examples where we're just going to look at the sentences and try and break them up into their structure. And we're going to use math symbols the same way that we know and love and have always used math symbols. So, again, doing exactly what we did over there, we're going to take some sentence and try to break it down to its logical structure. See, what is it saying? There is a number x less than 5 and greater than 3. What's that saying?
There is a number x.
Tell me what to write.
There exists
There exists.
x.
I think that red is working pretty well. Can you guys see the red okay from where you are?
Kind of hard to see.
It's kind of hard to see.
Shoot.
Is this a good one? Yeah. Okay, there exists x such that what?
X is a number.
We'll assume. Most times we'll assume that we know the domain here. We'll have a lot more to say about the domain later, where that x is coming from. But we're going to assume from context. And so it's understood that there exists x. We're talking about a number here.
So x, then you write x less than 5.
There exists x such that x is less than 5.
And x is greater than 3.
And x is greater than 3. Perfect. Now notice here that, just to be very clear, this less than symbol is a predicate.
Yeah.
It's a predicate that takes two terms. Now I told you that there's two ways that we can talk about predicates. So I did the taller applies to Jack and Frank, I think. Jack is taller than Frank.
Frank, son of Jack.
Whichever way. When we have a predicate that takes exactly two terms, we have a special name for those types of predicates. Can you guess what it is?
For two predicates.
If a predicate takes exactly two terms, we have a special name for it. Huh?
Compound.
No. Trying to get my discrete math student, since we've talked about these 100 times over and over again. A relation. It's called a relation.
Oh, yeah. That was
So there's a saying Jack is taller than Frank.
yeah, that's why I was bringing that up.
I know. So when it's a relation, when it's a predicate that takes two terms, we often use this infix notation. We often flank it with the two terms that we're talking about.
Yeah.
So There's no reason we typically use capital letters for predicates in this class. There's no reason that we have to do that. And for predicates that we talk about all the time in all sorts of different fields, we come up with special symbols for it. So we come up with this special symbol right here, the less than symbol. And everyone understands what this predicate is. And so then we flank it with the appropriate number of terms, x and 5. 5 there's a constant, x there's a variable, okay. So don't think that we're doing anything different just because now we're using a less than or a greater than symbol instead of a p or a whatever, or a t. So it still is just a symbol representing a predicate, same as any other symbol. It's just a special symbol. All right, so there exists x such that x is less than 5 and x is greater than 3. There's a number x less than 5 and greater than 3. Perfect. All right, let's try the next one. Given any number x, there is a smaller number y.
So for all x.
For all x, given any number x, there is a smaller number y.
So there exists y.
There exists y.
Where such that
Such that
x is less than y.
such that x is less than y. For every x, there exists a y such that x is less than y. For any number x, there is a smaller number y.
So that's it.
Now, we need to split this. X is greater than y. For every x, there exists a smaller y.
Oh, yeah.
For every number x, there is a smaller number y. Y is smaller than x, not bigger than x. But pretty close. All right, let's try this one. There is no largest number. That's a cool one.
For all n. For all x. Can we should we?
There's a couple ways you can write it, so.
X is not bigger than that.
There is no largest number. For all x,
There exists a y.
there exists a y
Such that y is bigger than x.
such that y is greater than x. Perfect. For every number, there exists another number bigger than it. There is no largest number. That was a cool one. All right.
Yeah, that was.
For any two numbers, x and y, the sum of x and y is equal to the sum of y and x.
There exists x and y.
There exists x and y.
That covers for any
That covers for any.
two numbers x and y. The sum, so such that sum of, so x plus y equals, in parentheses, x plus y equals the sum of y and x, y plus x.
The sum of y plus x. For any two numbers x and y, the sum of x and y is equal to the sum of y and x. Does that say for any two numbers? Or does that say there exist two numbers?
Oh, for every.
Yeah, we gotta switch this to a for all. And a for all. Right?
Get mixed up in any.
For any x and for any y, you can pick any two out in existence. It doesn't matter which two you pick. X plus y equals y plus x. If we do the existential, we're just saying there are two things in existence that happen to satisfy this rule. Whereas this is saying any two things in existence satisfy this rule.
Yep.
Okay. Next. There are numbers x, y, and z such that the difference of x and y is less than the product of x and z. There are numbers x, y, and z such that the difference of x and y is less than the product of x and z.
Yeah. So there exists x, there exists y, there exists z.
There exists x, there exists y, and there exists z.
Such that x minus y
Such that the difference of x and y, so x minus y,
is less than
is less than
x times x z.
the product of x and z, so x times z. And parentheses, perfect. There exist three numbers x minus z such that x minus y is less than x times z. It's not always the case, but you can find three numbers out there that satisfy it. All right. For every number x, there is a number y such that for every number z, if the difference of z and 5 is less than y, then the difference of x and 7 is less than 3.
So we'll start with for every. So that for all x,
All right, so you want to start with for all x,
there exists number y,
there exists y,
and such that why is it such that there? So just do for all z again.
huh? For all z,
Yeah. And then such that.
you sure?
I don't know.
Oh, okay.
I don't know why such that goes forward. But it seems like it's supposed to be another let part. Oh, if. No. Yeah.
I don't know, I just teach. I don't have to do anything.
If. So z minus 5.
Z minus 5.
What is going on with that if? Oh, yeah. So z minus 5 is less than y.
Z minus 5 is less than y.
Implies
Implies.
x minus 7 is less than 3.
Good. Let's do some parentheses here to make it a little bit more clear. Do bracket, bracket, parenthesis, 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 parenthesis. Perfect. For every x, there exists a y such that for all z, z minus 5 is less than y implies x minus 7 is less than 3. Oh wait, he uses if then. For all x, there exists a y such that for all z, if z minus 5 is less than y, then x minus 7 is less than 3. Perfect. Easy as pie, right?
Yep.
All right, let's try the next one. If the sum of two non-zero numbers, is 0, then the numbers, then one of, you can tell I was looking up at the clock when I was writing that. Then one of the numbers is greater than 0.
Okay. Then there exists. What is a quantifiers now? It's messing me up.
It is messing me up too.
The sum of two non-zero numbers is 0. So there exists x and y.
There exists x and there exists y, such that,
X plus y. Oh, and x and y are not equal to 0.
so what am I writing?
So 0 x y. That's using 0 as a predicate.
No, we're going to use math symbols that we know enough. Such that x is not equal to 0 and y is not equal to 0. Remember, our math notation is already using all this stuff. So you don't need to symbolize our math notation, it's already symbolized.
Okay.
So x is not equal to 0 and y is not equal to 0. Okay?
Can I see
Oh, sorry.
So then x plus y.
Do I put something before the x plus y?
I don't
So you just want an x plus y here?
know. No. Comma.
comma, we
And
don't have
and.
commas, and we can do that, that's something we have.
Oh, that first antithesis.
And x plus y
Equals 0.
equals 0.
Implies.
That all implies maybe
How do you show either?
put to help us keep track of our implication. Here's our antecedent, and then we'll have our conclusion here. What's our conclusion?
That x or y is greater than 0.
Oh, that's how you show either.
That x or y is greater than 0.
Okay.
Let's see. Y greater than 0, is that a formula?
Well, put x or y in parentheses. Is that what you mean?
Or it can only be applied to two formulas.
Oh, x is greater than 0 or y is
There we go.
Oh, okay.
X is greater than 0 or y is greater than 0. X is greater than 0, yep, that's a formula. Or y is greater than 0, yep, that's a formula. Or them together, that's a formula. Okay. And we got it. Almost.
No. What?
If the sum of two numbers, so first off, get rid of these quantifiers. Where did you ever justify that?
How does that modifiers just last time?
If the sum of two non-zero numbers is 0, so if x, let's read this literally, if x is not equal to 0 and y is not equal to 0 and x plus y is equal to 0, then x is greater than 0 or y is greater than 0. Isn't that exactly what this is saying?
Well, it's not.
Literally, that is exactly what it's saying.
Yeah.
And literally, this isn't a sentence.
Okay.
But we know in English that our universal quantifiers are often idiomatically implied or given to us idiomatically. It's implicit. It's just understood. So it's for every x and for every y. You took a random shot in the dark. For any two numbers, as long as they're not both 0 and their sum is 0, then one of them is greater than 0. That's true for any 2x and y, not a particular 2x and y. So when in doubt,
Use every.
it's universal. And you're pretty safe. Okay. So that was a good taste of, these were homework problems, by the way. I wanted to write them up in case I had time so that we didn't have to fight the projector. So we will call it there for today. Hopefully now you're comfortable symbolizing sentences. There's more exercises in the book that we didn't do. So if you want to do more of that, that's fine. And then next week we'll be moving on to more general proofs now, using this broken down notation.